let's go to our code and let me run this function. This is our previous example. This is second order, this example. And now I want to consider this charge distribution, and let's see if we can generate this result using our code. So I Control A, copy and paste. I write FEA try 4. So here we have this number of elements and number of nodes. Let me write here 2 elements, and this is xn, yn connectivity list. So the only difference is in the value of charge density. So here the charge density is not constant. The charge density is a function of x, so we should consider it in our formulation. So here you can see the way that we calculated the force vector for linear and quadratic mesh elements. Actually, we should solve this integral, right? This integral, right? In this case, rho is inside of this function, and we should be able to calculate F1 and F2. So you can use numerical integration methods to calculate this integral. Actually, in this case, rho is a function of x, and instead of this integral, we should solve something like this: minus LE divided by 2 integral of rho as a function of x times ni zeta or ni x dx. So we can use, for example, single point or multiple points. Actually, if you remember numerical methods or integrations, when we have a function here and right. So you can search, for example, Gaussian points for integration. If I write here Gaussian points for integration. So here you can see the formulation. You can approximate this integral by this summation. We have weights and the value of function at specific points. For example, if you want to use single point, 1 point, this is xi, and this is the weight function, 2 point, 3 point, and so on. So this is one way for calculation of integration. You can read this method in detail here if you are interested. So we should use Gaussian quadratures here. So in analytic solution, this is the value of d. I write here a function. Actually, in MATLAB, you can define handle functions also. For example, I write here f is a function of x. This is the syntax for definition of handle functions. For example, 2 times x plus 1. And as you can see here, f is a function handle. And if I write f1, this is 3, right? 2 times 1 plus 1, that is 3. So f is a handle function that you can use it. So I define here charge distribution or charge distribution as a handle function. I write here x. So you know that the value is equal to this function that we defined it here, minus rho naught times 1 minus x divided by d squared. So if I place a breakpoint here and run this function, so this is charge distribution, that is a function of x. So if I write here charge distribution 1, you can see the value. So here is the loop, and we should modify this part of the code by calculation of this integral. So I can write this something like this. This is not FE. Actually, I write here single point, and you can see the weight and point xi, that is 0 and weight is 2. So FE1 is equal LE divided by 2 rho naught divided by 2 times this. So for quadratic elements, that was for linear mesh elements, but for quadratic mesh element, that is different. This is the function that we want. So as you can see here, FI E is equal integral from x1e to x2e ni times rho v dx. So how we can replace dx by standard values? You can see the standard functions for the second order mesh elements, quadratic mesh elements. Here, this is map. So according to this, pick up this one. So you know that d zeta is 2 times dx, and derivative of this part is 0, right? So I can write d zeta is equal 2 times dx divided by length of element. So dx is equal length of element divided by 2 times d zeta. So, and you know this is from -1 to 1, but we have LE divided by 2 here. So if I replace dx by this term, I have LE divided by 2 integral from -1 to 1 ni rho v. This is a function of zeta, this is a function of zeta times d zeta, right? So here I can write FE1 is equal, these are our functions n1, n2, and n3. So what is the value of n1 for zeta equal to 0? It's equal 0, right? And what is the value of n2 when zeta is 0? It's equal to 0. Only we have n3, right? If we use single point, right? If we use single point integration method. So only we have n3. So I copy this, paste, paste. This is 2, 3, and this is 0. This is 0. But here we have a value. The value of n3 when zeta is equal to 0, xi is equal to 1. And what is the value of charge density? So this is L E I divided by 2 times 2 times charge distribution for what x? I write here xi. Actually, here we should use a reverse function, reverse map, right? So we are looking for the value of x when the value of zeta is equal to 0. So according to this, the value of x is equal zeta times x2e minus x1e divided by 2 plus x3e. So xi, or I write here x1 of integration method, is 0 times this expression, that is LE, divided by 2 plus x3e. That is actually xn of connectivity list of element I and 3. So this is x3 of E, actually this part. So I write this part also for clarity of the code. So I write here charge list of x1. So let's run the code and check. This is the exact solution, and this is the no. We don't have analytic solution now. Actually, the analytic solution is for previous case, and for this case I should update. Copy, paste, save. I write analytic solution 1. The analytic solution for this case is this one, right? So let's write here d to the power 2 rho naught. So I write here right, and this is correct. So you can see the answer here. This is the exact solution, and this is the finite element solution. But why this is different from this one? Because we used single point integration method. And what if we use higher order integration methods? For example, 2-point, right? So if I use 2-point integration method, you can see the value of integration point and the value of weights, right? So weights and integration points according to these equations that we have here. So let's implement 2 points and check the answer again. So if I use 2 points, I should calculate the value of x1 and x2 that are my integration points, x1 and x2. So you can see this is 1 divided by sqrt of 3 plus and minus sign. So I have minus 1 divided by sqrt of 3 instead of zeta. I am going to find the corresponding x, x1, x2. So you can see the value of integration. So I have this one, times. So what is n1? You can see the n1 here. We have n1, n2, and n3, right? n1, n2, and n3. So because this is a constant number, I can calculate it. What is the value of n1 when zeta is minus 1 divided by sqrt of 3? So let me write these functions here, n1, but because these are constant numbers, you should do them once. So I write here as a function of zeta is equal 0.5 times zeta times 1 minus zeta. Copy this, paste. This is n2, this is n3. What is the n2? Zeta times 1 plus zeta, and n3, 1 plus zeta, 1 minus zeta. 1 plus zeta, 1 minus zeta. So I can use n1, n2, and n3 in this integration. You can see the value of weight is equal to 1. So I should write here n1 of minus 1 divided by sqrt of 3 times charge distribution for x1, this integration point. The weight is equal to 1 plus n1 for this point, and this is x2. This is plus 1 divided by sqrt of 3. So I should copy this, paste, and paste this here. This is n2, n2, n3, n3. So let's run. As you can see, this is the exact solution and this is the finite element solution. Let me check. This is 1 divided by sqrt of 3 times charge distribution. Actually, this function, this summation, we used 2 integration points. The weight is equal to 1, and this is not 0.5. This is 1 plus zeta, 1 minus zeta. So you can see the value of function that we have here, right? So, but as you saw in Ansys Maxwell software, when we use one number of adaptive paths, we calculate something like this. So if I run the code, we calculate something like this. So maybe we need to increase number of integration points, for example, to 3, to be able to capture something like this. So this is our solution till now. So let's try if we use 3 integration points. So these are our xi and these are weights, right? So for 0 and 3 divided by 5 sqrt. So let's use 3 integration points. So I write here zeta 1, that is equal to sqrt of 3 divided by 5, copy zeta 2 and zeta 3. So this is plus, this is minus, and this is 0. So I write here plus, minus, and this is 0. What are weights? Weight 1 is equal 5 divided by 9. 5 divided by 9. Weight 2 divided by 9. And weight 3, that is corresponding to zeta 3, is equal to 8 divided by 9. So x1 is zeta 1, counterpart to zeta 1. This is zeta 2, and x3 is zeta 3. So as you can see here, these numbers are constant, and I don't need to put them inside this for loop, right? To be able to write a faster code. I will explain how you can write a fast code later, but here our focus is on getting a good solution. So here I should write w1 times this function x1 times, actually, n1, copy w1 times n1 of zeta 1 plus this is w2 zeta 2 x2 w3 zeta 3 and x3. Copy this, paste. So this is n2 and this is n3, and run the code. So you can see the value of function here. It seems we have an error maybe in our calculations, right? Because I think 3 points integration is enough, but here we cannot replicate something like this. So let's check. This is the function 1 minus x divided by d squared. That is the same as this one. 1 minus x divided by d squared. This is n1, n2, n3. 2 elements. What if I use 4 elements? No, we are not close to the exact solution. This is minus. So minus SQRT here, right? Let's calculate the electric field also. So this is calculate E for 1 degree elements. I copy this and paste it here. Calculate E for quadratic elements. Save. As you know, the procedure is totally the same. Just we need to calculate the value of corresponding reference coordinate. So this is the value of V and this is the value of E for quadratic elements, right? So just I need to implement this equation. So this is the value of zeta for quadratic mesh elements. I should calculate x3e, that is 3. So this is 2 times x3e, and we don't have this minus sign, right? This equation, 2 times xi minus x3e, x2e minus x1e, and then we should implement this equation. That is minus 2 divided by this expression here times V1 E times this one. So I write here, actually I can copy this and paste it here and write V1, V2, V3, this is Vn, right? This is our input here. So voltage of first, second, and third node of the mesh element. So I write V1e times, according to this equation, zeta minus 1 divided by 2, or zeta minus 0.5 plus this one. I copy this plus this one, V2e, plus finally V3e minus 2 times zeta, minus 2 times zeta. So this is the value of electric field. For example, in the second try, in this try, I also can plot the value of E for this second order, right? This is for our previous example. And now if I run this example, I can run this code and you can see the value of electric field when we have 2 mesh elements, right? So from 30 to around 5, from 30 to this point and this point then. So in the same code, if I increase number of mesh elements and run this code, this is the value of electric field. I think we have a mistake in our code because we have an offset, as you can see here. Okay, so let's check our solution with the Ansys Maxwell software solution. As you can see here, we have two mesh elements, and from report to the export desktop, I export the result to this file. I write here EX Maxwell in tab version, save, right? So from here, export, you can save the result. Also, you can specify number of points, steps, and something like this that we have here. So let me create an Excel file, open, also edit this Maxwell result, copy. As you can see here, we have this number of points. So I paste it here, and if I select these two columns, I can report this graph, something like this, or this one is better, a straight line, right? So this result is calculated by Ansys Maxwell software, and we have 1001 points. So let me here run this code. This is our solution, and I write here I want to use this function here, VFE. So instead of x here, I write here x is equal lim space from 0 to d 1001 points, the same as export of the Ansys Maxwell software, and run this. So here in the workspace, you can see the value of x and the value of VFE. So this is the value of VFE. I can copy, or I can write VFE is equal VFE transpose to copy this column, copy, and paste it here. So this is the Ansys Maxwell solution, and this is our FEA code. So let's delete distance, insert, and now we can compare, right? So as you can see, this is the Ansys Maxwell software solution, and this is our solution. Let's use two mesh elements and compare. To run VFE transpose. So let's pick up the answer from workspace and paste it here. So this is the Ansys Maxwell solution, and this is our solution. So we have an offset here. We should check what is the reason of this offset. Okay, I checked the M file, and this is the error. Actually, N1 is 1 divided by 2 zeta times zeta minus 1. But I wrote here 1 minus zeta. So if I run this code, as you can see here, we have an offset, but let's use the correct equation here. And if I run, as you can see, we can get the same answer that is reported here in this reference for non-uniform charge distribution, right? This answer. Okay, here also you can calculate the value of electric field and compare with this graph. So if I increase number of elements, for example, to 10, as you can see, we can generate a fine solution using the finite element method. Okay, so now you know the procedure for writing the finite element code considering quadratic mesh elements for non-uniform charge distribution. In our reference, the integrations for calculation of elements of load vector are done analytically. So you can see these equations here, equation 1.157, right? So these integrations are calculated analytically, but we used Gaussian quadratures and we calculated integrations numerically. And you can see we can get good results, and now the code is correct.